Recording. All right. Thank you. All right. So, sorry again for the technical issues with the tutorial. This was my fault for forgetting to bring the charger. So we will record it again sometime tomorrow. I don't worry. Thanks. No worries. Okay. So today we will start a new topic. As I said, there's one more lecture in these topics we've been doing before with continuous systems and stationary states. And I will add it. So that's the case of the box. So of the potential box with finite potential. So I'll do this in the extra lecture because it's more or less the same techniques. Of course, the insights are slightly different. But if there's one lecture that I don't need to do in person or live, it's that one. So before we start with spin, I just wanted to say one thing is in response to a question someone asked last time, which is like, okay, we have these stationary states. Right, so they look like this thing with which you could see as a superposition of a wave that is moving this way and one that's going that way, and then something here or decreasing depending on the energy and so on. But these states don't really evolve in time, right? They just get a phase. So how can we compare this to the situation that we actually have in the lab, which is we prepare something closer to a wave packet, right? So something like to this, where this is the envelope function, so it looks more like a real particle going there, right? And how do we compare things that came here? So we saw like the transmission coefficient, which is given by the amplitude of this wave here. The reflection coefficient is given by the amplitude of this wave here. How does it like reflect on something that we actually do in the lab, right? And so the idea behind it, I'll try to see if there's some exercise that is reasonable to do in the tutorial. But the idea behind it is that, well, we prepare a wave with relatively well-defined energy, meaning what? That we can write, so say we have our state psi with this wave function, and we prepare it in a way such that the energy is more or less well-defined, meaning what? We can always expand it in the energy basis, so it will be some integral of dE E, where these are these states, right? But we do such that it only has support in a very small region, so E or E plus delta. Okay. So meaning it lives in an energy shell E plus delta. And this one can do, okay? And this maybe we will have an exercise with an example so that you can actually write a wave packet as a superposition of energy eigenstates, right? And then how is it chosen? So we choose it such that like the transmission and reflection coefficients don't change too much for the states, right? These are continuous functions. They were not always monotonic, but for very small energy, they are more or less the same. And then what is happening to this wave function to this like particle as it arrives here. Well, you know, it comes here. It goes in this way, then I'll just then, you know, something happens to it here with a part of it going that way and a part of it going that way. And then if you wait enough time, it's going to be approximately, so this is the case of a scattering state, right? It's going to be approximately, again, a little wave function going this way and a little packet going the other way, such that then if we now put some detectors here, another detector here, right? So you send some photons and then you put a detector on the left and a detector on the right, okay? And the probability that it will click on the right is approximately given by the transmission coefficient for this energy shell, right? Because it corresponds to the amplitude of the wave here. And the probability that it clicks on the left is going to be approximately the reflection coefficient for this energy, which is 1 minus TE, right? In this case. So this is how we relate the things that we learned about stationary states to things that we can actually do in the lab. So what I will do is try to see if there's an exercise we can make from this, and it will depend on like how annoying the maths are for this to prove it. Okay. So now we can start a new topic, and that's exploring more spin is generalizing this idea of spin and seeing where this takes us. And first, let me just motivate it. So far, we only know spin about the electron spin with these matrices that are like Pauli matrices times a constant. But there's many applications of quantum systems with properties that are similar to spin. And what we'll do is to try to find a general approach to characterize them. So for example, if you talk about individual atoms, you can, I don't know, for example, I don't do spectroscopy or something to measure the energy levels of the atoms. This depends on the spin of the electrons in the atoms, for example. So we will look at this later. Spin. So this we'll see sometime next week. Another one is phenomena like ferromagnetism, meaning what makes a material a magnet or a material react to magnets. And the idea there is that you model the material, for example, your metal, as a lattice, right? And in every atom of this lattice, there is an electron spin that is relevant in the sense that the total Hamiltonian, it's going to be something like sum over I, some constant, the spin in the z direction for this atom I, times the identity on the rest. And this constant depends, for example, on whether there is a magnetic field and the field is. So for example, in the lowest energy, for example, they might all want to be down, facing down, so that they minimize this. Plus something like all the neighbors, right? All the neighbors of, again, some constant And now the product of the spins of the two tensor identity on the rest. And now this is something, so this in particular is the Ising model, and we can change it by saying, well, if I put the magnetic field in a different direction, maybe this is spin X and not spin Z or spin Y. Depending on the value of this constant, if it's positive or negative, this tells me if my spins want to be aligned or anti-aligned, for example. And a whole lot of solid state physics and statistical physics depends on Hamiltonians like this. You can also, there's some proofs of computational complexity that you can encode some kind of, is it NP complete? I think so, problems into the problem of computing the ground state of this Hamiltonian. So you can encode 3 sets into this in particular. So this kind of things are also used in quantum computing, for example, and so on. Right? Sometimes finding the properties of the material consists of finding the Hamiltonian, diagonalizing it, and looking at the low energy state. So in all these things, spin is important. But then, for example, we talk also about the Stern-Gerlach experiment, and you can do it with anything. So imagine that instead of throwing in an electron that we know, we throw in some other particle. Here there's a magnetic field, and then we see that it has 3 blobs here, right? Which correspond to spin +1, H, 0, H, and -1, H bar, instead of 2 for the electron. How do we model this kind of situations? What does it have in common with the spin that we already know, and so on? So this is the kind of things we do. And the other one that we'll see in next lecture is that spin is also very analogous to angular momentum and rotations in 3 dimensions. So it's really, really important in general. Okay. So how we'll go about this is the following. We take some properties that we know from of spin, and then we're going to generalize them to arbitrary dimensions. Okay, so it's going to be a bit like doing science fiction, in that we'll ask, oh, what if there was this small technology, how will this change society? It's going to be like this. We say, what if we have these commutation relations? What kind of structure do we get in the physics? So let me just recap what we know so far. So we started with the Pauli operation, polymatrices, right? And there were X, Y, and Z -1. And they had some properties. So they were Hermitian, meaning they're equal to the conjugate, the same for the others, for Y and Z. They were also what is called, it can't be involuntary. Okay, they have this property, X squared equals Y squared equals Z squared, which is the identity. Right, if you multiply them by themselves, they are the identity. These two things together mean that they are unitary, meaning if you have X dagger, that's the identity, and the same for the other two. Sorry? This and not being unitary, yes. Yes. I mean, you have many observables that don't correspond to physical evolutions, right? For example, X and P are Hermitian, but they are not unitary.
No, I mean, otherwise, the second property is fulfilled. It applies solution.
No. I think not, but let me think about it. Let me think about it after. It sounds weird. Because there's nothing here about the complex conjugate. So I don't know. You can find it. But then the most important thing were the commutation relations, and these were xy equals 2I z, and so on, yz equals 2I x, and zx equals 2I y. And the eigenvalues of these are plus and minus 1 for all of them. And then from here, we define the spin observables. So xx equals h bar over 2x, and so on. And we said, well, this corresponds to, for example, measuring the spin of an electron, which is modeled by a qubit, but the eigenvalue, I mean, the thing you actually measure is not 1 and minus 1, but it's h bar over 2 and minus h bar over 2. So now the one important thing that we'll keep from here is going to be the commutation relations of these observables. And this I'll write here. So the thing that matters and that we'll keep until the end is this: xy equals a h bar z, and this time I'll write all of them: sy, sz, h bar, sx, and sz, sx equals h bar. That's right. We'll keep this here. And now what we do is the following. We'll ask, oh, what if we had some Hilbert space H of a non-dimension and non-dimension. And the only thing we know about it is that it has these three operators that satisfy this commutation relation, okay? What if we have this technology? And what can we say about this Hilbert space? Okay? And what we'll do in the next, so today and in the next lecture, is actually find out a bunch of properties of this. So that's what we're gonna do. And it's kind of a long roadmap, but we'll get there. So the first thing is that we need to pick a basis to be kind of our computational basis, our default basis. And we'll pick, just like in the qubit case, we're going to pick the eigenbasis of SZ to be our default basis. So what do the eigenstates of SZ depend on? So there's going to be a state here. And it's going to have an eigenvalue, And just because we put this constant h bar here, let's assume that this constant is important. And then it should be multiplied by something. So we're going to call this m. Okay. And this is some m that we don't know. All we know is that it's a real number because these matrices, we also assume they are Hermitian. Okay, so then this eigenstate depends on m, so we call it state m. But it could be degenerate in principle, so it could depend on some other constant alpha that we don't know. So all I've said so far is that this operator that we determined, we just stipulated that it exists, and it has an eigenbasis. Yeah? And we call the states of the eigenbasis by m, which is related to the eigenvalue, and something else that does not affect the eigenvalue, right? So it could be degenerate on this. So if I want to draw the Hilbert space, so suppose it's a continuous case, I can write it like this. So here's the ZZ, and then there's different values for m. I don't know yet how many there can be. So for example, there could be an m here and some m prime. And then for each eigenvalue, there could be several states, right? So this could be m alpha 1, m alpha 2, right? Okay. And I know nothing, so I don't know how many eigenstates there are. In this direction, I don't even know if it's continuous or not. I don't know how many values m can take. We don't know anything. And what we'll be doing is to prove that actually they're kind of bounded. It's always the same. It's always the same level of the same degeneracy for all values of m, and you're going to bound the space vertically and horizontally. And this later will have applications to all the cases I talked about before. So the first step, it's going to be to define some operators. And we do this kind of in analogy to the classical case. So imagine that classically you have some vector with some x component and some y component, right? And then we can have R, which is the modulus of the vector. So here we're going to define this thing as squared to be the sum of all these observables, xx squared. So think of it really like analogous to, in the classical case, having the modulo of the vector, where now the components are the spin operators. It's an analogy with some limitations. So this we call total spin. And then the first thing we do is to show that it commutes with all the individual spins. X, Y, Z. And why do we do this? Well, if this is true, then they share an eigenbasis. So then we can, so if this is true, then, for example, SZ square of this which is then mh bar squared and alpha, which means that this state is also is an eigenstate of SZ and does not change the eigenvalue. Okay, so in particular, we can measure the two simultaneously. And I will first prove this claim, and then I'll tell you what we do with it. Don't do this. So this is more like a journey of discovery, or for a while you don't know why the guide is going this way, but just trust me. And in fact, it will only become clear next week. Today we're only starting. Okay. So we want to prove that thing. Let's do it for SZ, and for the others, for the other two, it's analogous. So then, well, what's this? So we have Sx squared, Sy squared, Sz squared. Oh. And the commutator is linear, right? So you get Sx squared, Sz, Sy squared, Sz plus okay, this one is 0. We know this, and then in general we're going to use this formula that we proved a few weeks ago. Which is when you have this commutator, this is a commutator of B and C plus AC commutator B. And what will happen is that they'll cancel each other out. So here we have Sx, Sz, right? Plus the second term, so this is Sx, Sz, Sx, plus Sy, Z plus Z, Sy. And now we can just replace them with those commutation relations, right? So that's so this is the opposite of what we have there at the end. So we get the minus sign, Sy. Now it's in the right direction, Sy, and then this Sx. And now here, Sy, H bar, Sx minus H bar Y. So if I did this right, oh, I missed something here. I left this one out. Let's just do. I left this one out. So, no. Sorry. Oh, yes, this is plus. Oh, this is plus, this is plus, this is minus, this is minus. Sorry. Yes, that's right. Okay. That's a plus. Okay, good. So then this one cancels with this. I'm missing an 8 batch I. This one cancels with that. That's it. There you go. Okay. Right. So now we believe that S square and SZ commute, which means that eigenstates of one are eigenstates of the other, which means that now what we'll do is consider the following subspace. So we consider subspace HS. These are going to be all the states Oh, span of all the states of my large Hilbert space that I don't know, that have the same, that are eigenstates of S with the same eigenvalue, okay? And I could put here an eigenvalue S that I don't know, and it would be any real number. But because we know where we're going, this will turn out to be look, remember that for now, this whole thing is just a number, right? I did not lose any generality by calling it h bar square SS plus 1. Okay. It will turn out to be very convenient to write it in this form. We'll see it later, okay? But so just think of, we have the total Hilbert space, and we kind of divide it into subspaces which correspond to the same eigenvalue of S squared. Okay? This is equivalent in, I don't know, to take like the whole space in R2 and divide it in kind of spheres. Oh, circles in R2 that correspond to the same radius, right? So here, this would correspond to some S of radius, and this would be S prime, and this would be S pi prime. And then the whole space is made by the direct sum of these things. Don't worry about it for now. Okay. So that's what we're doing. Okay. Why are we doing this? Because it's going to be it's going to be easy to characterize each of these HS individually. So the first thing we'll do is now to define two new operators, which are called the ladder operators. So plus, we define it as Sx, S minus S x minus I S y. If for, remember at the very beginning, we chose the basis of Sz to be the default basis. If we had chosen X, then we would put different operators here. So in the claim now, that will do, and that will prove today, is that when I apply S plus on some eigenstate of Z, I'll get another eigenstate of Z multiplied by some constant that we don't know yet. Okay. But corresponding to the eigenvalue m plus 1. And that when I do the minus, there's going to be some other constant, which can depend on m and alpha, don't know yet, m minus 1. And why would this be useful? Well, because now we have for every S, so if you have the m's here, if we start in an eigenstate of Z with this eigenvalue here, we can apply these operators. S plus to go up. That's why they're called ladder operators. So this is kind of, it's called a raising operator. We go up, and we can use the other one to go down. So, and then what we'll do later, tomorrow, on Tuesday, is that we find the very bottom of this, which is going to correspond to S equals minus S. The very top is going to be plus S. So you find the very bottom here, and then we'll apply this S plus to kind of construct the whole Hilbert space all the way up, get to the top, and we could also apply the S minus to get the Hilbert space all the way down. Good. But now we need to prove this claim. Okay, so we'll do the first one, and the second one is analogous. And first, just a note that is not part of the proof, but it's also a technical note, so it comes here, is that so this S plus and S minus are not Hermitian, but when you do the Hermitian of S plus, it's going to be S minus. So this is S X plus minus SY plus, right? Because it's a conjugate, the I becomes minus I, but these two are Hermitians, so it's just SX minus I SY, and that's just S minus. And equivalently, S minus conjugated complex transpose conjugate is S plus. Meaning, look, these operators are not necessarily Hermitian, not necessarily unitary. So this constant here might not be 1. But they are the inverse of each other. Right, so if you apply this to reverse this operation, you'd apply that, which already tells you that these constants are going to be kind of inverse of each other. Okay. But we want to prove this thing here. So first we look at the commutator as always. So far, so good. As that S plus. Well, that's as that as X plus I as that as Y. Oh, what is this? Well, this one is I H bar S Y. And this one is minus I H bar S X. So this whole thing is just H bar S X. So we get back the original operator. Okay. So that was step 1. Good. Step 2. Oh, that was step 2. This is step 3. Well, so we know that if you apply this on some state, some eigenstate, you get H bar M right? In general. So now we want to know what happens to, what about this state here, right? And the claim is that this is an eigenstate, maybe not normalized, but an eigenstate of SZ. Okay, so then we need to see, well, what happens when we apply SZ on this? Do we get something like that? Well, but now we apply the commutator there. So we have A times B equals B times A, and then a term that's given by the commutator. So this is S plus SZ plus H bar S plus. Right, this just comes directly from there. And now we still have our state here. So we have two terms, right? Think of the first one. You have SZ applied on this. It just gives us the S plus is still here, but now we have this HM eigenvalue. And then the state comes again. So let me just write it here. M alpha. And now H bar S plus M alpha. It's nice to be back to discrete math. So then we have H bar M plus 1. And now comes S plus alpha. And this state here is the same as we started with, right? So it just tells us SZ applied on this state equals a constant times this state again, which means that this green state is an eigenstate of SZ. With what eigenvalue? H plus M plus 1. Okay. And so the conclusion is that S plus M alpha, well, corresponds actually to M plus 1 alpha. But there could still be some constant here that is not 1. Okay. Because then that constant would appear here, but also here. Right? So if I say that this is, what did I call it? K times M plus 1 alpha. And this is K, alpha prime, M plus 1 prime. Right, this would, the whole thing would still be the equation for an eigenvector. Right, so this is a constant, which we don't know yet. And this alpha in principle can be can be an alpha prime. We know nothing about it. So know that at this stage, SZ, like these M numbers, could still be continuous. All we know is that this operator S plus kind of jumps in discrete values between them. Okay. So it could be that these are all the possible values of M, and that if we start here and apply S plus, we go there, we go there, and we still miss out on everything in the middle. But it will turn out not to be the case. And we'll see this later. So analogously, you can do at home that SZ commutator with S minus, it's going to be minus H bar SZ. So when you plug that in here, you get that SZ S minus and alpha equal to H bar and minus 1 S minus and alpha which means that S minus M alpha is again an eigenstate of SZ with eigenvalue n-1. It can change the other factor that we know nothing about, and it can have a new constant here that we still know nothing about. Okay. So now what we have is we have this Hilbert space HS, which is kind of an eigenspace of our operator S squared. And here, for the same value of S, so fix S, and S, remember, is this S squared that inside the same fixed S, we can have different values of M. And this is the same idea that, even if you have a vector with a fixed radius, you still have some freedom in choosing the Z component, right? So if I have this vector here, Z is 0, but if I have this here, I have Z equal minus S, if S is the radius, here I have Z equals plus S, and I can get everything in between. So that's kind of the idea. Now, in the next lecture, we'll bound this vertically and horizontally, like I say, meaning we'll find that actually M can only value in this value, just like in the classical case. And we'll find that horizontally, where is it there? They all have the same number. So the M equals the M took M in this interval. And we'll find that M is discrete. And then this will tell us about properties of particles and atoms and whatnot. Yep. But I'll stop here and you'll continue in the next class. When it comes together, it's actually quite nice. And remember that, we started from something very, very simple, just those commutation relations. That's the only thing we imposed, and that they were emission matrices. We imposed nothing about dimensions or anything else, any other property. And we're going to already discover quite a lot. Okay. So thank you. See you on Tuesday, and I'll upload the other lecture when I have time. Okay. So in terms of content, it's the continuation of the last one. So it's stationary states in 1D. And in terms of where I missed it, it was 4 weeks ago. Yeah. And in terms of order in which you should watch it, it does not affect the rest of the semester. So it should be okay. And it is important for the exam. So.